Degree of freedom. Freedom means the relaxation, means no obstruction, no resistance, no hindrance. You are walking on boundary wall, and that's quite narrow one, quite thin. It's not wider. Then if you are walking on the boundary wall, you'll be having the freedom to move along one axis only. Your degree of freedom of movement there is one, means you are free to move along one axis. Suppose some old person is walking on the floor of his room. He has the freedom of movement too. We talk in terms of axis only, because he'll be having the freedom to move along X or Y. It could be two-dimensional only. So we will say that that old man has the degree of freedom of motion too. Why I excluded youngsters and children? Because they would have the temptation of even jumping also. That's why we excluded, and I consider the example of old man. Now consider bird. Bird could fly along all the three axes. So birds will have the degree of freedom 3, means they could avail all the three axes for flying purposes. This is the actual sense of degree of freedom. Now the number of ways an object can move, it will have similar number of translational kinetic energy as well. So what is degree of freedom for the molecules? It is simply the number of ways, independent ways in which a molecule could possess the translational kinetic energy. Listen again. The degree of freedom of molecules is the number of independent ways in which it could possess the translational kinetic energy. But here we are not considering the rotation and vibration. Only translatory motion is considered. Then in that case, we talked about X, Y, and Z. Similarly, we will consider rotational motion as well. You see, when we consider monatomic gases, the degree of freedom will be only 3. Monatomic gases, no bonding, no force. That means there could be no rotation, no torque, no vibration. In monatomic gases, only the translatory motion will be possible. So, degrees of freedom in monatomic gases is going to be 3 only. Then, rotational degree of freedom. Rotation is possible with diatomic and triatomic gases only because forces are there because of the bonding. You see, if rotation is possible about 2 axes, you'll have 2 degree of freedom associated with the rotation. It could be even along 3 also. Then vibration. Vibration degree of freedom is normally considered at higher temperature. At lower temperature, we do not consider vibrational degree of freedom. Then Maxwell also suggested one important law that's known as Maxwell's law, equipartition law of energy. It says every degree of freedom is associated with the translational energy half RT, but this is per mole. At the same time, you could say the degree of freedom is associated with the translational kinetic energy half kT. Remember, this is kT, but now you'll say per molecule. Per molecule, when you talk about molecule, it is K. When you talk about mole, it is R. So, R is molar gas constant. For R, one term is used, that is molar gas constant, whereas K is known as Boltzmann constant. So most popular name for this, Boltzmann constant. But do remember this analogy that R to mole and K to molecule. That's why you could also say Boltzmann constant is nothing but molecular gas constant. This is gas constant for one molecule. This is gas constant for 1 mole. So I hope you'll remember another name of Boltzmann constant. It is molecular gas constant. And K could be calculated dividing molar gas constant by Avogadro's number. Now we'll consider one by one all the three cases, that is mono, di, and triatomic gases, using the equipartition law that every degree of freedom is associated with the energy half kT per molecule, half RT per mole. Say it's a monatomic gas. Degree of freedom only translational, that's why only 3. So, energy is going to be 3 by 2 RT. For monatomic gases, the energy will be 3 by 2 RT. This is energy. Now, CV, later on we will study. While studying specific heat, we will see the derivation also. The molar specific heat at constant volume is given by du upon dt. So, du upon dt. If you differentiate, you will find 3 by 2 R. Cv is equal to 3 by 2 R. You know, Cp minus Cv equal to R. This also we will study in thermodynamics. Cp minus Cv equal to R. If Cv is this much, Cp will be 5 by 2 R. That means by just knowing the degrees of freedom, you know the complete horoscope of any gas. You know the internal energy, degree of freedom, Cv, Cp, gamma, so many quantities you know just simply by knowing the degree of freedom of a particular gas. If you consider diatomic gas, diatomic, then obviously 3 translational degree of freedom will be there. But along with that, there will be 2 degree of freedom concerned with the rotation. Overall, it becomes 5. And then in that case, the energy is going to be 5 by 2 RT, because degree of freedom is going to be 5. Then in order to find the value of CV, you'll divide it by T, it becomes 5 by 2 R. And then in order to find Cp, it will be 7 by 2 R. Similarly, if you consider triatomic gases or even polyatomic gases, there you have to be alert, a little precaution is needed. You have to check whether the structure is linear or non-linear. If it is linear like this, linear triatomic gas like CO2, it is linear structure. Degrees of freedom will be there 3 plus 2. Only 2 degree of freedom with the rotation. Overall, it becomes 5. Then again, Cv equal to 5 by 2R and Cp 7 by 2R. But at the same time, if it is H2O, H2 is not linear, it is non-linear. In that case, degree of freedom will be 3 for translation and 3 for rotation as well, overall amounting to 6. Then Cv is going to be 6 by 2R, that is 3R, and Cp is going to be 8 by 2R, that is 4R. So you notice that degree of freedom go on increasing, that way Cv will go on increasing, Cp will go on increasing, but gamma will reduce. With the increasing atomicity of the gases, gamma reduces. Gamma is equal to, you see, Cv is going to be n by 2R. In general, Cp is going to be F by F plus 2 by 2 R. F I am showing for degree of freedom. Degree of freedom. If F is the degree of freedom, you are getting F by 2R, as in the case of monatomic. it was 3 degree of freedom, you got the value of CB 3 by 2R. So again, I am generalizing the whole thing. If degrees of freedom is F, CB F by 2R, CP F plus 2 by 2R, and gamma becomes equal to CP upon CB, that is F plus 2 upon F, that means 1 plus 2 upon F. Wonderful result you have before you, that you increase the degree of freedom, gamma will decrease, and moreover, there is going to be one linear relation between gamma and 1 upon F if you compared it with the equation straight line y equal to mx plus cu.